Good afternoon, everyone, and welcome to the PhD and MSc Fusion Open Day, organised jointly by the UK Atomic Energy Authority and the Fusion Centre for Doctoral Training. We have 8 separate universities lined up today for you to speak to about potential PhD and MSc opportunities in fusion research. And we have a very exciting agenda lined up for you, starting with some introductory talks on different areas of fusion research. And then moving on, you'll be able to visit individual university stands. You can enter a student chat room and talk to existing PhD students. And you can go on virtual tours of fusion research facilities at Cullum Science Centre, which is a world-leading centre for magnetic fusion research. The web links for all of these activities are in the agenda, which has been emailed to you, and so hopefully you all have that at hand. You'll see that, as usual, in this Zoom webinar, there's a Q&A function, so you are invited to submit questions as we go via the Q&A facility. There may not be much time to answer the questions at the end of each talk, but we will be collating all questions and producing a written question and answer record, which will be emailed out to you after the event. While the questions are being submitted, you will be able to see all questions that have been submitted. And so you can upvote any questions that you like, and they'll go to the top of our priority to be answered, if possible at all, during the session. If you have specific questions that relate to a specific university, you should reserve those for your separate Zoom sessions with the relevant university. In this first webinar part of the event, we're looking for questions related directly to the talks, which you'll hear, or more general about PhD opportunities. So let's get started then. And first of all, I'd like to invite Professor Howard Wilson, who's the Fusion CDT Director, to give you a brief introduction to fusion research.
Okay, good afternoon, everybody. I'm now going to see if I can share my slides. Okay, so you should be able to see my slides now. So I'm going to give you an overview to fusion research and the capability in the UK. This is a very strange event, sitting in my son's old bedroom here instead of standing in front of you in the lecture hall in Cullum like we usually do. But I hope this will be useful for you, and I hope you understand why we have to do it this way. We should thank Cullum Centre for Fusion Energy, UK Atomic Energy Authority, for co-organising this with the Fusion Centre for Doctoral Training today. So I'm going to go through these things in the next 15 minutes. I will tell you, in case you don't know, in case you've forgotten your A-level physics, what a fusion reaction is that we're trying to exploit, the science associated with that, some of the benefits. I will then look at the pathway to fusion, look at the 2 approaches, very briefly, magnetic and inertial. You'll get more detail on those later this afternoon. And then I have a slide at the end on fusion education in the UK. So the reaction that we are trying to exploit is a reaction between 2 heavy forms of hydrogen, 2 isotopes of hydrogen, tritium and deuterium. If we can bring them close enough together, they fuse to give us a neutron and helium and lots of energy. If you weigh your neutron and helium, and you weigh your tritium and deuterium, you find you lost a bit of mass, and that mass, as Einstein tells us, goes into power energy. So deuterium is plentiful. About 1 in every 6,000 hydrogen atoms is in fact deuterium. So there is plenty of deuterium that we have in in water, for example. Tritium, however, is rare, and so we have to make it on site, and we make it by reacting the neutron that comes out with lithium. And lithium, of course, is plentiful. You'll find it in rechargeable batteries, in particular laptop batteries, for example. So we interact that neutron with lithium, another nuclear reaction, gives us the tritium, more helium, actually, and more power. And then that tritium, then we can react with the deuterium. So we have this sort of nice closed cycle once we get the reaction going. We have to put all that inside a box, and the different fusion mechanisms are largely about what are the different kinds of box that you put that in. We have broadly two boxes, one to keep the plasma in. So we'll look later what a plasma is. It's basically to make these two things react, we have to reach temperatures 10 times the temperature at the center of the sun, 100 million degrees. And at those temperatures, pretty much everything is in plasma state. So we need something to confine that plasma. And then we need a blanket in which we capture the neutron, we react it with the lithium, and we remove the power. So they're the essentials of a fusion reaction. And from that, we get the products, electricity, but also other ways of using that, the heat that we can get out of the fusion reaction. Why have I done a bath here and a laptop battery? Well, basically, if you take the energy that you get from the lithium in a laptop battery and the deuterium that you can get out of half a bath full of seawater and fuse it, then you will get all your electricity for your lifetime's needs. That's one important message. The other one is don't Google man in bath. This is the benefits of fusion energy. You'll have seen there was no mention of carbon in that cycle I've just shown you. So there's no carbon dioxide, no greenhouse gases. It's inherently safe. It's very difficult to do. So anything goes wrong, it just goes out. Provides a base load supply. We can operate it when we like, independent of the conditions in the vicinity. And as I've just argued, there's abundant fuel. Sounds brilliant. The snag is it's hard. It's very hard. So let's look at some of the reasons why it's so hard. To make fusion happen, we have to bring this deuterium and tritium nuclei really close together. They're both positively charged, of course, so they don't want to come together. The way we achieve that is we heat them to very high temperatures, as I said, 100 million degrees, that's 10 times the temperature at the center of the sun. That then accelerates them to very high speeds, and they slam into each other, overcoming that Coulomb repulsion and giving us the fusion reaction. As I've already said, at these temperatures, the gas becomes a new state called the plasma state. It's a state where the electrons are effectively stripped from the nucleus. So you have a gas, an ionized gas effectively, whereas the gas in this room, everything is, the particles are all largely neutral. The gas in a plasma are made up from positive ions and negatively charged electrons. Collectively, they're all neutral. If you add up all the positives and all the negatives, you will still get a neutral state, of course, but individually they're charged, and so they undergo Coulomb interactions, and those Coulomb interactions mean that a plasma behaves in a rather different way to a neutral gas, and therefore there is a whole research industry around understanding the plasma state. To confine that plasma at 100 million degrees, there are two principal techniques, and you'll learn about them this afternoon. One is magnetic confinement. I think it's fair to say that that's the most advanced towards a fusion energy reactor at the moment. It's the one I'll spend most of my time on this afternoon, but also inertial confinement, and you'll hear a lot more about this from Tony Arbour later. Magnetic confinement, the most advanced magnetic confinement facility is the Tokamax. And this is a particular Tokamax. This is the ITER Tokamax, which is being built in the south of France. It should start producing its first plasmas around the middle of this decade. It's been built with over 15 billion euros of investment by more than half the world's population, or countries representing more than half the world's population. And it is designed to produce 500 megawatts of fusion power. That's for putting 50 megawatts into the plasma. So it will produce 10 times more fusion power than power that goes into the plasma to heat it. That's important politically, of course, it's an important demonstration, but actually it's an important scientific milestone to try and achieve as well. Let me just talk you through some of the components of a Tokamax. So here, this pink ring, this pink donut is the plasma. So this will be our deuterium and tritium fuel confined by a magnetic field. That magnetic field is created by this set of D-shaped magnets, coils that go around the donuts. That gives us what was called the toroidal component of the magnetic field that goes around this direction here. We also have another component of the magnetic field that goes around the plasma, that goes around this way, and we create that by putting a toroidal current through the plasma. And we put that toroidal current through the plasma by this solenoid, ramping the current in the solenoid, changes the flux, the magnetic flux through the center, and induces, by transformer action, induces a current in the plasma. It's a final set of coils, and that's these purple ones that you can see here that that actually loop around. This is just a cross section. They loop around. They're rings that go around the plasma. These are the Ploidal field coils, and they shape your plasma. You can see this vessel is D-shaped, and the plasma cross section has this same D shape. We found in the 80s, actually, this was very good for the confinement and the stability of the plasma. There are a bunch of ports, and those ports receive the heat. There's 50 megawatts that I told you about that we will need to put in to heat and control the plasma, fuel the plasma, and also, for a research scientist, the diagnostic instruments that look at what's going on inside that plasma all have to access through these ports. You'll hear a lot about the walls, the materials in the wall that we will place inside ITER. This has a big impact. Of course, these are in a pretty extreme environment, high heat fluxes, high neutrons, but also they can have an impact on the plasma, as we found out in JET recently. So there's some interesting physics associated with those. The blankets that I mentioned, they come in at the edge here and they capture the neutrons as they come flying out from the fusion reaction. And then finally, all of that heat that's being generated in the plasma has to be managed somewhere, and it's managed in this exhaust system, which we call the diverter at the bottom of the vessel here. I like this diagram. It shows where we've come, and it more or less shows where we've come since I was born. The Tokamax was invented in Russia. I won't tell you when, but it was more or less the year I was born, within a few years. It was called T3. It sat on a temperature scale, which I can show you along here in kilo electron volts. If you don't understand kilo electron volts, they're just the same as they're just proportional to Kelvin or Celsius, if you like. The sun sits here, so this is 10 million degrees Kelvin. Up this axis, I have a product of temperature and density, which you'll understand, and something called the confinement time, which is how effective your confinement system is. For magnetic confinement, we have typical confinement times of about a second. That's not the same as the pulse length. I'll tell you about that later if you come to the CDT stand. It's not the same as the pulse length, but it's how effective the magnetic field holds onto the confinement. So that's about a second. It's a relatively long confinement time in a magnetic confinement fusion device, but we have a modest density. Whereas inertial fusion goes to really, really high densities and short confinement times, such that this product will be the same for both. So this is where we sat back in the 50s. These curves are important curves. This curve, where I put Q equals 1, this says that I get the same amount of fusion power out as heating power in to get the fusion conditions. Okay, so if I was talking about ITER with its 500 megawatts of fusion power, this would have 500 megawatts, need 500 megawatts to heat it, huge amounts. Ignition up here is I need no power in. The fusion reaction will be self-sustaining. I don't need to put anything in. And so between those is our ITER line, which is the Q equals 10 line. Okay, so this is where we're trying to get to for a commercial fusion reactor. A factor of 10, 100, 1,000, 10,000 above where we were in the 50s, 60s, and a factor of 100 in temperature. So if we go into my teenage years, that people were very excited about this Russian Tokamax, and they were built Tokamax all over the world. So Aztecs was in Germany, TFR in France, T10 was the successor to T3, PLT I think was in the US. And you see immediately there's a factor of 10 increase in temperature and in this so-called triple product. Go into the 80s and 90s, when I was a sort of similar age to you, and I started working at Cullum in 1988. You see the likes of JET coming online, D3D. These are Tokamax that are still operational today. Aztecs Upgrade in Germany is still operational. D3D is in San Diego, by the way, in America. Some of them have stopped operating now, like TFTR, but now you see we're reaching the temperatures. This 100 million degrees is not the issue. It's this confinement time is the issue and getting up here. Then through the 1990s, JET in particular and the Japanese Tokamak JT60U were starting to knock on the door of this Q equals 1, this sort of break-even goal. That then guides us to how big do we have to build ITER to get sufficient confinement time to be close to this ignition line. And so this guides where we're aiming for with ITER. This is the ITER site. As I say, it's really cracking on now. This is where the Tokamax will sit. To get a sense of scale, if you look down here, you can just see some little cars, lorries. So it's a huge site. So that's looked back to the past. You want to look to the future. Where are we going in the future? Well, this is the European roadmap. And so you can see lines on this representing ITER, as I've just been talking about, going into the future. Let me put some times on it. And you see that ITER first plasma is around the middle of this decade, but full deuterium tritium performance is about 10 years away yet. In parallel, we are designing DEMO now. So DEMO is a demonstration reactor which will produce net electricity, and it's looking to produce net electricity towards the end of the 2050s into the 2060s. You'll learn that materials are really important, and we need to build a materials irradiation facility to understand those. We, the European community, not so much in the UK, but we, the European community, are looking at something called the Stellarator as a backup option. And then there are lower cost innovations, lower cost concept improvements and innovations that we're looking at. In the UK in particular, we're pushing these quite hard. And so this is just 3 examples, and 3 nice examples, because it shows a national programme, so-called STEP programme, which has £200 million of funding from the government, led by UK Atomic Energy Authority. It's in a feasibility study at the moment. That is £200 million to demonstrate the feasibility of this reactor concept by 2024, looking to put electricity onto the grid in the 2040s. Then there's private companies who have got interested in fusion, and investors have got interested in investing in fusion, which is very encouraging. Tokamak Energy are looking to put energy on the grid with their so-called Spherical Tokamak, a concept device, making use of a new technology, high temperature superconducting magnets, to get really high magnetic fields. And then finally, another company based in Oxfordshire, First Light Fusion, is adopting an inertial approach to fusion energy. Again, trying to bring the cost down and accelerate the timescales to delivering fusion. This is a nice diagram because it shows how STEP interacts with the full international programme and also builds on the breadth of capability that we have in the UK. I don't have time to go through the figure in detail, but these circles down here represent technology facilities that cut across magnetic and inertial fusion. So we have at UKAA on the Culham site, we have the robotics so-called RACE facility. We have the materials research facility. We have a so-called heat facility looking at tritium science, a whole range of fusion technologies, and of course, high performance computing. And those things cut across no matter what your fire is, whether it's inertial fusion or magnetic fusion. We also have coming online, particularly to magnetic fusion in January, the mass upgrade Tokamax after a £55 million upgrade. This is unique in the world. There isn't another Tokamax like this. And we are hoping that it would guide the way through ITER, I've already talked about, through IFMIF donors, which is this irradiation facility, to STEP, trying to bring STEP forward to around the 2040s. Inertial fusion has some similarities in terms of the technology to magnetic fusion, but the key difference is how you create the fusion reaction, and it's created in most schemes, not all of them, but by high power laser facilities. In the UK, we have the Central Laser Facility at the Rutherford Appleton Laboratory, actually also close to Culham. I've shown here the pictures of Vulcan Laser and the Gemini Laser. But also we have AWE operate the Orion Laser, which has 15% academic facility time. Again, we have access to international machines, and probably the most famous one is NIF, which is aiming to achieve ignition at some stage. Let me just close with a few words about the education programme in the UK. First of all, there was a review done a few years ago, 3 or 4 years ago now, of all of the fusion education programmes in Europe, and the UK came out as top, the only one to score 10 out of 10 in those fusion education programmes. So I can honestly say it is a world-class, we have a world-class fusion education programme. On the right here, we have the universities, and this shows you an ever-growing number of universities that are involved in fusion. So probably it's changed since I drew this diagram. And in fact, Brian pointed out that I'd missed one out even yesterday that has come online, come and join the family, if you like, this year. So a growing number of universities, a very large number of UK universities involved in fusion. And we have a large number of doctoral programmes associated with those. I'm the director of the Centre for Doctoral Training, which is a coordinated doctoral programme, which I think Roddy will say a bit more about in the talk following me. You know, we all work together. We are a collaborative bunch, trying to make sure that fusion happens. There are also master's programs associated with general nuclear energy, but also in particular, we have the MSc in fusion energy that we operate at York. It's not just about the universities though, it really does start at school. So although I started over here at the right, you know, we in the Doctoral Training Centre, for example, realised that we have to get people excited about fusion at a very early age in order to make sure that we have a diverse community that can support fusion, and everybody feels that fusion is for them. Nobody's excluded in fusion, and that message needs to start at school. So we engage quite strongly with schools, and then also apprenticeships. And this is a new apprenticeship building that's just being constructed on Culham, the Culham Science Centre there. So that's all I was going to say. Just let me close though with a slide showing you what's happening this afternoon if you're not aware. There are a set of talks that will follow mine on specific aspects of fusion, the webinar talks, running through to about 2:45 this afternoon. In parallel, each of the universities, and you can see the logos of the universities that are involved this afternoon over here, so that we will have a bunch of stands, and you should have received by now the links that will give you access to those stands. I'm going to be on the Fusion CDT stand, so if you do want to come and talk to me, please come to the Fusion CDT stand, and I can answer any questions about the presentation I've given, as well as the Fusion CDT. We have a student chat room if you want to go and chat to some of the PhD students that are already involved in the fusion. I think we might have a master's student there as well. I don't remember, I'm afraid. And then also we've arranged 2 sets of virtual facilities at the UK facilities, one around the Tokamax, one around materials and engineering. They will run in parallel, and there'll be 2 of them. So in principle, you could go to both of them. One will go from 3 o'clock till 4 o'clock, and one will run from 4 o'clock till 5 o'clock. Okay, so I think that's all I wanted to say. I don't know if we have time for questions or not, Brian.
Okay, thanks, Howard. We don't actually have any questions uploaded directly on the talk. Hopefully, the prospective students found that very exciting, and it's whetted your appetite now. If you didn't already realize it, hopefully now realize that the UK and is a major player on the world stage in terms of fusion research. And as Howard pointed out, many universities are involved in that effort. So we're now going to hear 4 talks digging a bit deeper into some specific aspects of fusion. And we're going to start with a talk by Professor Roddy Van from the University of York, who's going to tell us about Tokamak plasmas.
Thanks, Brian. Yes, my name's Roddy Van. I'm an academic at the University of York. I'm just a few doors down from Howard's in normal times. And yeah, I've got the opportunity to tell you a little bit about Tokamak plasmas. As part of my job at York, I'm also the program director, so responsible for the academic program for the Fusion Centre for Doctoral Training. And I'll say something a little bit about that towards the end of this talk. So I hope it's okay. I'm just before I talk about plasma physics, just very briefly, I want to repeat a quote that this chap here, Chris Clellan-Smith, made at the York Plasma Institute some years ago now, but I go back to it again and again because this is really the reason that I do fusion rather than anything else, is that fusion solves a big problem. I know Howard talked about this, but I wanted to repeat this point. And Chris Clellan-Smith said, the biggest challenge of the 21st century is to provide sufficient food, water and energy to allow everyone on the planet to live decent lives in the face of rising and increasingly urbanized population, the threat of climate change and eventually declining fossil fuels. So why do I work in fusion? Why do I recommend that you pursue a career in fusion? It's because you have the opportunity to solve through doing science, and for that matter, associated areas as well, economics, politics, and so forth. But particularly by doing science, you get the opportunity to address this massive societal challenge. But why? What are the other reasons for doing a fusion PhD or MSc? Well, as well as, and I say as well as saving the world, but this is hardly hyperbole. In fact, there's also a really great bonanza, is that the best word? A really great variety of exciting and interesting science. I don't want to make comparisons with other areas of science, but fusion really is extremely broad. The fact that it goes all the way from highfalutin, I'll talk about turbulence in a minute, sort of turbulence theory, all the way to very, if such a spectrum is like this really exists, all the way to really heavy duty big engineering and everything in between, simulations, experiments. and across a really wide range of disciplines. So just some of them are listed here. Plasma physics, I'll say a little bit more about in this talk. There's a whole load of engineering, including building these big vacuum vessels. Heather's going to tell us a bit about engineering later. We've got lasers. We use these in Tokamax for diagnostics and for other things, but Tony Arbor will talk in the next talk about inertial confinement fusion as well. We do stuff with high power microwaves and in fact low power microwaves for diagnostics. In some Tokamax, massive capacitor banks are used for startup. The temperatures are really high. Some people would argue that in a tokamak, although Tony might disagree with this in the next talk actually, but in a tokamak, you get the highest temperature gradient from tens of millions of degrees to very close to absolute zero within a meter or two. So huge temperatures and massive temperature gradients. Materials challenges, so the materials get really hot and they get bombarded by neutrons. See what Annika's going to say later. We do some massive computing simulations. Tokamak plasmas are hard to simulate, so we need big computers. There are also some generic theoretical physics challenges. So there are some questions that we can pose about how general physics works, which are well explored in a tokamak. There's overlap with other areas. And the other thing, of course, is if you want to travel the world, then join an international physics community. When I first came to York, I was on the back end of an independent research fellowship. And in fact, I had a conference in Colorado 10 days before a conference in Japan. And the cheapest way to get there was to have a 3-day layover in Hawaii. So not putting on one side the ecological footprint that I left behind, do international physics and you get to see the world. Okay, so just as a brief reminder of Howard's description of a tokamak, here is a picture, in fact, of a spherical tokamak. So a little bit different from what Howard said, but the topology, in fact, is the same. How does a tokamak work? So a spherical tokamak, let's focus on that. And I focus on that probably because it has the simplest structure. Indeed, I stole this slide from Howard. We have two sets of magnetic fields, if you like. We have what we call the toroidal magnetic field, which is shown in black here, and that's generated by a steady current going vertically through this rod. That current is of the order of a megaamp and generates a magnetic field of the order of a Tesla. And then additionally, we pass a ramped in time current through a solenoid, which is wrapped around this central rod. That induces an EMF in this direction, which then induces a current in this direction. The plasma has very low, but nevertheless finite resistivity, finite resistance. So that generates a current in this direction, which then generates a field in what we call the ploidal direction. So round, if you like, the short way round the donut in this direction. And that combination of ploidal and toroidal magnetic fields is what makes a tokamak a tokamak. That combination of magnetic fields is better both for confinement, that is to say, keeping the particles in the plasma, and stability, so stopping the plasma wobbling around in such a way that it hits the wall. One thing I've missed out the second bullet, which is kind of important. Why do we use magnetic fields? Well, because if the particle is sufficiently cold, if it's sufficiently slow moving, then the particle gyrates around the field line, and in the orbit of that gyration is fairly small compared to the size of the plasma. So those relatively slow moving particles travel along field lines like they're like beads on a string. And the idea about having a toroidal configuration like this is that the strings, the magnetic field lines, don't have ends, so they can go round and round in this direction and that direction, and they stay within the plasma. But the problem is that this only works partially, as I'll explain. So on the next few slides, I've got a few. Now, I've had to be rather selective, but on the next few slides, on this slide and the next few, I've got some examples of perhaps arguably some of the most interesting, most challenging aspects of tokamak plasma physics. Okay, so the first highlight that I've picked is turbulence in magnetized plasmas. Why is this really important? So it's because of the turbulence in tokamak plasmas that they lose heat as quickly as they do. It was thought, so Howard talked a little bit about the history of tokamaks. Back in the early days, people didn't appreciate that the plasma would be turbulent, or at least as turbulent. So people imagined that tokamaks might be relatively small. The insulating thickness that's required, it turns out, is dominated by the turbulence destroying the insulating property of the plasma. And so the type of the turbulence and the properties of the turbulence determine how big the tokamak has to be. This is a long-standing fundamental scientific problem. People started describing plasma turbulence, people like Kolmogorov back in the 40s, I think, certainly 50s. So there are lots of questions which still aren't fully understood about how turbulence in magnetized plasmas work. Why is it so challenging? Well, one of the reasons is that you've got to consider at the same time, you've got to consider hugely differing length scales. So the ions and electrons gyrate on, so the ions gyrate on a relatively large scale and the electrons on a relatively small scale. And also there are different time scales. So the electrons go round much quicker than the ions. But on top of that, you've also got the timescales associated with the evolution of, and I'll put this in the next bullet, in the evolution of large-scale flows and the equilibrium itself. So modeling this, developing models for this and computationally simulating this is extremely challenging. And there are questions which are long-standing, which still aren't understood about how turbulence works in tokamaks. So both on this slide and the next, well, on this slide, I've talked about confinement. And actually what I mean by that is the challenge that comes when we don't have confinement. So as I said a couple of slides ago, relatively cold or slow moving particles are generally fairly well confined, as long as you set up this toroidal field and this ploidal field correctly in some sense, then slow moving particles are generally fairly well confined. But the problem in fusion, well, one of the problems in fusion is that there are actually quite a lot of particles which are traveling really rather fast. Where do they come from? So superthermal, is it super or supra? But anyway, particles traveling faster than the thermal speed. Where do they come from? Well, from the fusion reactions themselves, of course. An alpha particle from a fusion reaction is traveling at about between 10 and 20% of the speed of light. Sorry, that's not true. The alpha particles are moving rather slower than that. The neutrons are traveling that fast. My apologies. But the alpha particles are still really shifting. And so they themselves move rather quickly, but they also collide with other particles, and particularly the electrons in the plasma. So those particles definitely have velocities well above the background plasma thermal speed. But also, in order to get the plasma going, so Howard had his diagram showing where we're trying to go. In order to get a plasma sufficiently hot that it's a high performance machine, we have to inject power, and that doesn't uniformly heat all the particles in the same way, and we often end up with tails in the energy distribution of particularly fast particles. And why is this a problem? Well, this is a problem for a number of reasons. There's one bullet I haven't put on here, that these particles can resonantly excite waves. I'll perhaps talk about that a little bit on the next slide. We certainly don't want jets of these superthermal particles going out and randomly blowing holes in the side of the vessel. A recent challenge, something we're very interested in looking at the moment, is the fact that although the toroidal is to lowest order symmetric in this direction, in modern tokamaks, we put in 3D perturbations to that field to increase the stability, but this makes the particle confinement more complicated, and we want to know. So this is this image on the right is a simulation for ITER. In fact, one of my PhD students has done, showing in lots of different colors, showing the orbits of lots of particles, and he's been figuring out in the 3D fields that ITER will use where for enhanced stability, whether some of these fast particles are going to go out and hit the wall. And in fact, how do you optimize those 3D fields to both get the stability you want and also to maximize the confinement of those important fast particles? So the next challenge is stability. So confinement is about basically keeping the particles in the plasma. Stability is about trying to stop a perturbation to the plasma from its intended state, which can limit the performance of the plasma. So, for example, back in the early days of tokamak physics, people used to see things called sausage instabilities, for example, where the plasma ends up with fat bits and thin bits, looks like a string of sausages, and the problem is the fat bits eventually hit the vessel wall. There are now we can deal with that now by the way we set up the magnetic field, but nevertheless there are now a bunch of perturbations which we see which limit the tokamak performance. I've put just two examples here, and these two images both relate to that first bullet. A particular concern are what are called edge localized modes, or ELMs. These are eruptions of the plasma surface, which in fact are filamentary in nature. This was really cool, actually. This was predicted in theory and then seen in experiment from really fast cameras. So this plasma, a few tens of microseconds before, was looking nice and quiescent. This is a picture, sorry, I've put from MAST upgrade. It's not from MAST upgrade, this is from MAST. mass upgrade's predecessor, showing the D alpha light from the edge of the plasma, and the plasma is burst out with these filaments, and this eruption only lasts 10 to 100 microseconds, but during this time several percent of the total stored energy can be lost. So this is really bad, and it's also really bad if you care about something on the vessel wall here. So we're working both with experiments and with simulation. So here's a simulation of some filaments coming out of the edge of the plasma from the BAT++ code to understand why these plasma eruptions happen. And this still isn't tremendously well understood in certain ways. Another, I haven't got any images of this, but just to give one, there are many instabilities we're worried about. But another is the so-called neoclassical tearing mode. This is where the magnetic topology changes, and we get little magnetic islands in the middle of, so they happen typically in the middle of the plasma, and they flatten the pressure gradient and can really dramatically degrade the plasma performance. Okay, I should accelerate a little bit. Perhaps another highlight that I've picked out, or another challenge, is the plasma exhaust. So if we look here, so I've got, these are two cross sections from different machines. This is Alcator CMOD, which sadly was recently, just a few years ago, was shut down at MIT in the States. And on the left, we've got a cross section from Mast Upgrade. So we've got the plasma in the middle with the field lines which are closed, going around a combination of this way and that way. And then when we go out this so-called last closed flux surface, the magnetic field lines are no longer closed inside the plasma. Their closure goes outside the plasma. But particles which go over this last surface, they can very quickly escape down the field lines and bash into the wall here. Now, we know roughly where they're going to end up, but it means that the surfaces here get much more heat than the surfaces over here, for example. And it turns out that the area over which that heat is deposited can be very small. And this can be, well, Annika's going to talk about some of the materials challenges, but this is definitely demanding for the material. So what can we, the plasma physicists, do to try and mitigate this, this materials challenge? Well, we can try and expand the field lines. Well, sorry, I should refer to the Mast Upgrade picture, because this illustrates some of the things we can do. We can try and spread out the field lines. So you can see that the field lines are very bunched coming through this gap. But they're more spread out here, and so that spreads out the way in which the plasma hits the plate. But also we can do something rather clever called detachment, where we actually stop the plate, even though the field lines go through like this, we stop the plasma itself hitting the plate by having a large neutral density in front of the plate here. And so, yeah, I should have said this picture on the left shows a thing called the Super X configuration. This configuration down the bottom is called the Super X configuration, which is one of the real priorities for the Mast Upgrade experiment. Another challenge, and this definitely crosses over with engineering, but is on heating and current drive. So typically the plasma doesn't produce, the heating is kind of the easy bit. We can stick in heat fairly straightforwardly often. I mean, I don't want to oversimplify it, but often. But typically the more challenging thing is that sometimes the plasma doesn't generate its own current where we want it to. So we have to additionally drive external current. This is achieved in a number of ways, sometimes using beams of really rather energetic particles of the order of 50 to several hundred keV. But often we do it using microwaves. This happens to be an interest of mine. This is a picture on the right of some Cullum folk and some folk from Oak Ridge National Lab who were doing some experiments with this gyrotron and with some others a few years ago now to get the plasma going using microwaves. And because I'm talking, I'm allowed to say a little bit about microwave physics, and the microwave interaction between microwaves and plasmas is really interesting from a fundamental point of view, because it turns out that the refractive index of a magnetized plasma depends both on the polarization, so whether the E field is vertical or horizontal, let's say, and the direction of propagation. So birefringence, metamaterial type properties of group velocity going this way and phase velocity going this way, this sort of thing is routine in plasma physics. So it's pretty cool science. But there are big opportunities coming up in the UK at the moment, because we've got, it's increasingly likely that on Mast Upgrade we'll see some high power microwave injection systems. So I think I've got about 90 seconds left. It perhaps goes without saying, but I wanted to say explicitly there are lots of opportunity for working in diagnostics, instrumentation, real-time control of the Tokamax to try and react to an instability, for example, is really important. And I mean, I've done a massive disservice just having a single bullet down here, but you'll have picked up that simulations, both for understanding diagnostic data, but also for simulating doing the Tokamax plasmas predictably, is really important. We use some of the biggest computers in the world. So I'm going to whiz through these slides so Brian doesn't get too cross with me. It's a really exciting time in magnetic confinement fusion. We've got Wendelstein 7X in Greifswald in Eastern Germany. This has been operating for a few years ago now. Bit different from a Tokamak, but nevertheless a magnetic confinement device. Really exciting machine. We've got mast upgrade. We've mentioned this probably a bit already. So this is probably okay. So it's just started operating now down at Oxfordshire. Down at Culham in Oxfordshire. We've got ITER, which Howard spoke about, but I just want to emphasize this is the most amazing thing. This is not an artist's impression, right? These are real people, and this is a real photograph. And this is just one segment of the vacuum vessel. This could be an urban myth, but I think the biggest lorry in the world with something like a little over 200 wheels was built for transporting some of the ITER components from one of the ports in the south of France up to ITER. I mean, in other news, we've got Pegasus at the University of Wisconsin is just finishing its upgrade. There are people in the UK working with that experiment. The STEP, which Howard mentioned briefly, which is a massive national, well, and international, but with a particular national focus project to study the feasibility of building a power plant in the UK. We've got the Japanese machine, JT60 Super Advanced, I think this stands for. That's coming online very soon. We've got JET preparing for a deuterium tritium campaign. There's lots going on. Brian, I'll be 30 seconds. I just want to have a very quickly brief you on the EPSEC Centre for Doctoral Training in Fusion Science and Engineering. I think that didn't fit on the slide. As Howard might have said, I'm not sure, this is a collaboration between York, which is the lead institution, and Durham, Liverpool, Manchester, and Oxford. All students across these 5 universities take, whichever university they're registered at, take core modules at 4 of the 5 universities. When you join one of the 2 strands, either materials or plasma. You do a bunch of core, what we call broadening modules, initially that everyone in the program does, and then you go and do more in-depth modules, either in materials or plasma physics. Those taught modules are mostly front-loaded in the first 6 months, and that's of the first year of 4 years. It's a 4-year program. And then we have some really cool stuff going on as well that's separate from the taught modules. We have an international workshop each May with some really cool speakers, some very high-profile speakers. We have a collaboratory, it's a bit like a mini placement in the 2nd year, and we also do some really cool outreach. Brian, hopefully I haven't gone on too long, but I'll finish there.
Okay, thanks very much, Howard. Roddy, thank you for that. Certainly, that's fine. We can move on now to Professor Tony Arbour from the University of Warwick, who's going to tell us about one of the other main approaches to developing fusion, namely inertial fusion energy.
So, hello everyone. Where am I? There we go. Hopefully you can all see that. I was going to chat through, we've had quite a bit of discussion about magnetic confinement fusion, which is the most advanced fusion technology that's been worked on over the last 5-6 decades. What I want to do in this one is just discuss inertial fusion energy. We know from lots of the background talks, and hopefully you all know, that the basic idea is to fuse deuterium and tritium. We get an alpha particle and a neutron, and that releases the energy. To do this, we require a temperature of about 10 to the 8 Kelvin. Howard, in his introductory talk, mentioned the importance of this equation that I have here, which is NT times Tor subscript E. This is called the NT Tor triple product. Not very complicated to derive, but it comes from just doing a quick estimate of how much energy you get out from a reactor, depending on how well energy is confined inside the plasma, such that you combine all of that to say, well, what do I have to do so that I actually get more energy out than I've put in? And you balance that out and you end up with this relation, which is the NT Tor triple product, where N is the number density, the ions T is the temperature, and this thing Tor E, which is central to much of fusion research, is the energy confinement time. That's the characteristic time scale that energy would leave the system if you stopped heating it or maintaining it, not the plasma confinement time. But we know what the temperature should be, so that's about 10 to the 8 Kelvin. So this actually gives us a relation between number density and confinement time. And in Tokamax, the aim is to run with a low density and a long confinement time. In inertial confinement fusion, the aim is to run with a very high density and a very low confinement energy confinement time. And in fact, the whole aim of this is to not bother trying to confine the plasma at all. So it's only the finite inertia amount of time that it takes for something to move apart that is the confinement time. I want to explain that in a little more detail. We assume that what we have is a sphere of deuterium tritium with radius r. Then we know from our relation here that what we've got to do is get this product of number density times confinement time bigger than some number. It doesn't matter what the number is at this time. So if we suddenly half the number density by doubling the volume, if we were satisfying this before, we're no longer satisfying it now. So as a rough estimate, we say that if we've got this deuterium tritium ball and it's hot enough, it's at 10 to the 8 Kelvin, once it's expanded, just because it's moving at the thermal speed, everything's just expanding out. Once the radius is increased by about 25%, the volume will have doubled, density halved, and we're no longer satisfying that condition. And the time it takes for it to move through 1/4 of the radius is r over 4, quarter radius, just divided by the thermal speed. That's how fast everything's moving. We put that into our NT triple product. We know the temperature, we now know the confinement time, and we end up with the relation between the number density and the radius. And if we multiply the number density by the average mass of deuterium tritium, we have a relation between the mass density, rho, and the radius, r. And so for inertial fusion, the key thing is to get this product of the mass density and the radius larger than some number at the same time as having the plasma at 10 to the 8 Kelvin. Now, if you think about that for a while, you could easily just have this to be the mass density of gas deuterium tritium, but then to satisfy this, the radius has to be enormous. And the problem there is that the amount of energy released can't be controlled. So in order to keep the total energy released from fusing deuterium and tritium down to a level that the vacuum vessel can hold, we only use a very small amount of deuterium tritium, which means the radius of this sphere is tiny. Consequently, the mass density, rho, has to be enormous. And so that's the challenge. The challenge we're stuck with is that it turns out when you stick all the numbers in, that you have to take deuterium tritium and increase it to about 1,000 times solid density at about 10 to the 8 Kelvin. And we do this through these 4 steps here. This is the most common way. It's not the only way, but it's the most common way. In blue in the center here, we would have our deuterium tritium fuel. The browny orange color on the outside is some plastic, and the arrows are lasers, which are uniformly illuminating this plastic. That makes the plastic heat up, so the plastic blows off. There has to be an equal and opposite reaction, so the blue fuel gets compressed. As it gets compressed, it approaches the 1,000 times solid density that we need, but also, while compressing this material, we also heat it up. So by doing this, we compress and heat it all at the same time until we finally get to a fuel of deuterium tritium, which is 1,000 times solid density and above 10 to the 8 Kelvin. Crucially though, since the heating is due to the compression, if we were to try and compress this slowly, what would happen is that just thermal conduction and radiation would mean that it would cool down. So what we have to do is do all of this sufficiently quickly that the fuel is compressed 1,000 times solid density and 10 to the 8 Kelvin faster than it would cool through radiation and conduction. You put all of those bits and pieces together and you end up with the basic requirements that you need for laser-driven fusion. So here's our diagram again. We're starting with a fuel pellet wrapped in plastic or some other material, irradiating with a laser, plastic ablates off. The back reaction causes the fuel to compress. It compresses and heats, reaches ignition temperature, 1,000 times density. We satisfy that relation and we get more energy out than we put in. We put the numbers in order to get a gain of 10 so that we have 10 times more energy out than we put in. And each single pulse of this process, 1, 2, 3, 4, releases about 100 megajoules, which is about the limit that you could do and still contain that amount of energy in the vacuum vessel. That all gives us that we need to get, as we said a few times, about 1,000 times solid density and a fuel of about 10 to the 8 Kelvin. But we have to do it quickly so it doesn't cool down. We're trying to heat it up. We don't want to Did it very slowly, did it quasi-statically, it wouldn't heat up because conduction would just take the heat away. So we have to do this at about 350 kilometers a second. That's about Mach 10. The drive time when we do that, because these things are just a few millimeters across the initial pellet, is about 20 nanoseconds. You can then estimate the amount of energy that you need to drive onto the outer shell to do that, and you end up with about a few megajoules of laser energy and a peak laser power of about several hundreds of terawatts, which is tens of thousands of large power stations connected in series. But obviously, it's only over 20 nanoseconds. The peak pressure that you get in this, once the fuel has begun to burn, is about 10 to the 5 megabar. And remember, a bar is roughly atmospheric pressure. So this is 10 to the 11 atmospheric pressures. And that's quite handy because the buzzword that we use for this is that this approaches petapascal scale physics. If you just look at this velocity divided by the time, you also realize that this involves an acceleration of the pellet of about 10 to the 12 g. So the acceleration is enormous. To an extent, this really encapsulates the whole problem. Imagine you had a balloon, small balloon filled with water, and you had to compress it to 1,000 times solid density. Obviously, if you just do it with your hands, the balloon would just squish out between your fingers. So this compression has to be done completely uniformly. It has to be completely uniform and spherically symmetric at the velocity of 350 kilometers per second in 20 nanoseconds. And that's the challenge for laser-driven fusion. Here's a sort of cutaway part photograph, part diagram of the largest laser facility that's ever been built to try and do this. This is NIF, which stands for the National Ignition Facility. It's in the Livermore Laboratory in California. It has 192 beams, so a sense of scale on this is that these are American-sized cars. So this is enormous. We have 192 lasers. You see the laser beams coming up here bunched up into quadrants. This has about the right amount of energy and it's got the right wavelength. So all the laser energy bounces backwards and forwards through here, and then through these pipes, through mirrors and reflectors, it comes down into a central vessel where we do the laser experiment. This particular experiment, however, doesn't fire the laser directly at the pellet as I'd shown before. Instead, what we do is we have a system where you fire the laser at the inside of a gold cylinder. It's usually gold, it can be another material. It's called a Hohlraum. And what happens is that laser energy is then converted into a thermal bath of X-rays, which fill this volume. And that happens just by Bremsstrahlung radiation. There's a couple of advantages for that. One is that this is now a much shorter wavelength than the incident laser, which means it hydrodynamically couples energy to the pellet more efficiently. And also, this thermal bath of X-rays that fills this volume is more uniform. Remember, the whole problem, one of the central problems is trying to get this compression to 1,000 times density symmetrically, and this is a way to try and make it smoother and more symmetric. And this is a typical target. It's actually quite an old one. But you see, we have plastic, we have deuterium, tritium, ice. In the center, there's deuterium, tritium gas. So we need solid and gas to coexist. So this has to be at the triple point of deuterium, tritium. So we start with a cryogenic target, and then we drive through with various shock pulses in order to try and get the compression that we want. A view of the inside of there are two holes this size. So here we have some standard size American scientists. So this is the size of half of the laser facility. And inside the vacuum vessel, the target goes on the end of one on this thing here, this huge looking pencil thing. And you can see the scale of the vacuum vessel. There's some two scientists getting in order to do some maintenance work. And the lasers come in through these laser entrance holes. Other holes are diagnostic ports scattered around. Because remember, there are 192 beams coming through, and there are diagnostic ports. So that's the scale of the experiment, which is aiming to try and get ignition. It was hoping to get ignition quite a few years ago, but failed due to some really quite unexpected physics, some of which has now been addressed. And so it's possible that this may still reach ignition in the next few years. And this facility fires twice a day. The actual target looks like this thing here, this little gold cone, and inside that is a millimeter capsule. So all of the energy from all of these lasers is focused down in 20 nanoseconds into a little pellet which is sits inside that. So that's the scale of the sort of experiments that we're working on. The physics issues involved with this is just some of them, is that we have here the plastic ablated deuterium tritium ice and deuterium tritium gas, and we want to compress it, which means that up until the last nanosecond or less than nanosecond, we want to keep this gas in the center as cool as possible so that we can compress it. So that's called the low adiabat. That's a measure of the temperature. So we have to keep this cold up until the very last bit where we heat it up. We need to get the velocity very large so that we can compress it and heat it faster than it cools. We need to keep it symmetric, so we need to have good shape control of the laser driving. And we also need to be able to stop higher energy components of the X-ray field that we might get from walls or lasers penetrating in, causing mixing of impurities. These 4 criteria here, these are the things that we need to control to try and get ignition, excuse me. And so doing that, we've got various control parameters. We control how we make the material. We can control the laser profile, the type of laser. We can control the thickness of the target. We control how things are pointed. And so we have this huge parameter space in order to optimize. This is an idealized case. There are actually many more complicated physics issues, which are usually often basic plasma physics issues before we even get to trying to optimize the sort of, this is like the engineering optimizing space, because this defines the number of control parameters that we have. So where would this go with PhD projects? The universities around the UK, apologies to anyone I have missed. These are the usual suspects of universities, some of whom have stands that you can go and look at after this talk in today's virtual open day. And they will have a series of opportunities. These will be on basic plasma theory relevant to inertial fusion. A very big deal is high performance computer simulations. By high performance, I mean running codes that require maybe 130, 140,000 computer cores at once working in parallel, running for days in order to do simulations. These groups between them are involved with experiments in the UK. The UK has extensive laser facilities, but the Rutherford Laboratory and AWE. In the US, there are 2 major laser facilities, the Omega in Rochester in New York State, and the one that I've shown you, the National Ignition Facility in California. There are experiments in Japan, in the EU, something called LMJ, Laser Megajoule, which is in Bordeaux, and there's lots of facilities being built in China. And across these groups, we have experimental PhDs across all of those facilities. The other thing to note about this, and this also applies to, I think, to the same degree to the people who might be interested in tokamak physics, is that the theory and simulations and many of the experiments are actually basic plasma physics experiments. So it's not just inertial fusion energy. The laser plasma theory that you require to do inertial fusion energy is also the same thing which is being developed at these universities for the next generation of particle accelerator. The idea here is to have compact tabletop proton accelerators for radiotherapy, for example, or electron sources or X-ray sources for imaging. So medical imaging, radiotherapy, industrial imaging devices, all industrial applications from the same theory that is a subset of inertial fusion energy. The other thing which has come up a lot in the talks is the fact that we need this temperature to be hotter than the center of the sun. We also need it to be 1,000 times solid density. So the conditions of matter which are generated in these experiments only normally exist in extreme astrophysical environments. So you can study astrophysical jets, you can study the state of matter in the center of a gas giant in laboratory experiments now. And so there's a whole branch of laboratory of astrophysics which is connected with the IFE research across all of these universities. So that's it for my sales pitch for inertial fusion energy. if anyone is interested in following up these, all of these, most of these institutes will have sessions for you to join later on this afternoon. If not, then you can look them up on the internet later. Okay.
Thank you very much, Tony, for that very interesting talk. We haven't any open questions at the moment. Questions have been coming in as speakers have been talking, and we've been dealing with them in the Q&A box. But we're ready to move on now to the next speaker, and that is Dr. Annika Khan. Annika is from the University of Manchester, and she's going to tell you about materials research for fusion. So, Annika.
Thank you very much for the introduction. I'm just going to share my screen, so hopefully you can all see that. So yeah, as Brian mentioned, I'm Annika Khan, and I'm from the University of Manchester, and I'm going to be talking a bit about materials for nuclear fusion. So I'm sure you've seen this before, but on Earth, the most efficient fusion reaction for commercial energy production is the reaction between two isotopes of hydrogen called deuterium and tritium. And that's because they have a higher cross-section or likelihood of reaction compared to other reactions within a similar energy range. Now, the products of this reaction are helium and also very high energy neutrons, which have an energy of around 14 MeV, which is a fusion-specific challenge that we as material scientists have to deal with and investigate. I'm just going to also talk a bit about ITER, which other people have mentioned before, which is this collaboration in the south of France, which Howard mentioned. And it's going to be used as a kind of a testing bed for a lot of different materials that we might use as well. So I'm going to use this kind of to put things into context. So first of all, if we look at the size of ITER, it's absolutely massive. So this is a diagram here of the reactor, and you can see that the radius of the tokamak itself is around 6 meters, and in height it's almost 30 meters, and the whole size of the reactor is almost 30 meters as well. And you can see the little person in the bottom right hand corner as well, just to put things into perspective in terms of size, which is also a big kind of materials and engineering challenge. Building something on this scale is yeah, very challenging. So now I'm going to talk about the specific materials issues for fusion reactors. So as I mentioned on the first slide, we have these 14 MeV neutrons, which cause damage on materials that we might use. On top of that, the heat loads are very high within fusion reactors. And as has been mentioned, in the center of the plasma, in your tokamak, you're going to have temperatures 10 times hotter than the center of the sun, so around 100 million degrees. We won't have that temperature at the edge where the materials will interact with the plasma, but it's still going to be very, very hot. On top of that, within the fusion community, we've decided we don't want to have materials that will result in high-level radioactive waste. So the materials we choose are often limited because of this, which adds another challenge. I've mentioned the helium as well, so how that interacts with the materials we choose is also something that we need to look at. The interactions between the plasma and the materials is also an area of research, and also generating those magnetic fields to confine the plasma is also a big challenge for material scientists. I should preface that we've just had to talk about ICF. I'm focused more on the magnetic field confinement side of things, but yeah, it's a big challenge for us. I'm not going to go into these in a bit more detail to kind of go into the specifics of each one. So with the 14 MeV neutrons, if you imagine your neutron is kind of like a snooker ball which comes and hits your material, and then the little atoms in the material are like the other snooker balls, and they hit each other and cause a damage cascade of different types of defects. So you can get like vacancies and self-interstitial atoms, for example, shown in this diagram here. And these kind of small scale interactions at shorter time scales then build up, and at a larger length scale and time scale, they have impact on the engineering performance of the materials we choose. And going from that small scale to large scale is a big challenge for material scientists. Another thing is having a source of these 14 MeV neutrons. We currently don't have a materials testing facility where there's these specific 14 MeV neutrons to test materials. So we often use different surrogates. So we can fire ions or protons at materials as well. So kind of if you imagine the orange particles here are neutrons and they hit ions in the sample, and those ions hit other ions, we kind of bypass the neutron and just implant ions to hit other ions in the sample. So that's one of the techniques we use to mimic this neutron irradiation. And we use a whole suite of different analysis techniques to look at those materials. But as I've mentioned before, the sample sizes are quite small. So going from that small scale to large scale is one really key area of interest. Also, there's a lot of modeling that goes into this, so molecular dynamics or dislocation dynamics as well. They're all areas that I've been looking at to model this 14 MeV neutron damage. If we then go on to the heat loads that we might experience in a fusion reactor, I feel this slide puts that into context, and it's really surprising actually. So on the left hand side, you've got a HWR nuclear reactor, a re-entry vehicle, and a Rolls-Royce Trent engine, and these all kind of face different lower heat loads than the diverter, which has been shown to you previously, which is kind of just like the exhaust of the Tokamak during steady state operation within ITER. So even just normal operating conditions, the heat loads are phenomenal. During operation, we could have things called transients within the reactor, and those are orders of magnitude higher than steady state operation, and even higher than the heat loads that you'd see in arc welding or even in a rocket, for example. So really high heat loads. And again, we're doing a lot of desiccated experiments on materials to see how they cope with these heat loads, doing high heat flux testing. So UK AEA are setting up a high heat flux testing facility at their new site up in Rotherham as well. So really exciting kind of progression on that side of things as well. As I mentioned, that we want to use low activation material. So depending on where in the reactor you are, there's kind of different materials you can use depending on the neutron dose those materials will receive. But this is some models that have been done for a demonstration fusion reactor, so demo reactor in the first wall region. And basically we want to avoid any of the orange materials. So having such a limited choice, again, is a big challenge for material scientists and engineers when developing materials for fusion reactors. This is in another area. So this is in the blanket shield region. And as you can see, you have a bit more of a choice of materials that you can use. But it's a big design constraint that we need to face. Then, as I mentioned, the helium exposure. So I'm going to specifically just talk about tungsten because that's an area of research that I'm interested in. So tungsten is the candidate material for the diverter region, which I've mentioned before. And when it's in the bottom of the reactor, it will kind of be exposed to helium. And the damage really varies depending on the fluence of the helium and also the temperatures that it faces. So at lower temperatures, 600 to 700 Kelvin, you get things like nanobubbles. At higher temperatures, up to 1900 Kelvin, you get this really cool surface modification, which is called fuzz. And it's kind of like a nanostructure on the surface of your tungsten, which turns it completely black. So it's the darkest known man-made metal that's ever been produced. So although that might be kind of an issue for fusion reactor design in case it breaks off and erodes, etc., interestingly, this material has potential in other industries. So photocatalysis, solar panels, gas sensors, things like that. So one cool thing about some of the materials research, even though it might be an issue for fusion materials, the crossover into other industries where it actually might be a positive thing is quite a nice side product of the work that we do. And then, yeah, at the higher temperatures, you can get voids in the tungsten as well. But the main thing is these microstructural modifications, they then can influence the mechanical properties, the thermal properties, fuel retention, which is another key area of interest. Obviously, we're using tritium. We don't want that to be stuck inside places where it shouldn't be. A, because we don't want to have radioactive waste, and B, we don't have that much tritium to play around with. So yeah, that's another area that's quite interesting. And then, as I mentioned as well, you have plasma material interactions, which is again another key area that we're looking at. So when your plasma interacts with all the kind of first wall and diverter components, it can erode the material. That material can be carried through the plasma and redeposited somewhere else. It can generate dust, which might be detrimental to plasma performance. As I mentioned before, it can influence fuel retention. It can cause bubbles, blisters in your materials, and then eventually embrittlement. So it's really important that we investigate materials so that we know we won't compromise the structural integrity of a fusion reactor. And then if we move on to the magnetic fields, so there's kind of two parts to this. So first of all, it's generating magnetic fields that are strong enough. What materials do we use to generate those magnetic fields? So in ITER, for example, they're generating magnetic fields with an intensity of around 13 Tesla. And to put that in perspective, a PET scanner is typically only 1.5 Tesla. So again, huge times greater magnetic fields. So one of the things that people use are superconducting magnets to generate this. So in ITER, they're using supercooled superconducting magnets, which is, I think, also kind of highlights the extreme nature of a fusion reactor. So you've got these supercooled superconducting magnets at the edge of the tokamak, which are almost absolute zero. And then in the center of your plasma, you've got temperatures 10 times hotter than the sun. So in the space of a few meters, you've got a temperature gradient that's not seen anywhere else in the universe, going from almost absolute zero to 10 times hotter than the sun is very crazy, and kind of, yeah, sums up the extreme nature of a fusion reactor and the challenges we might face as material scientists. One interesting development that's occurring at the moment is the development of high temperature superconductors. So there's some fusion companies that are looking into this, such as Tokamax Energy in the UK, and then in the US, there's the spark reactor as well, if we want to make use of this new technology. So again, that's another really interesting part of the material science research that's being carried on at the moment. Another big impact that we have to look at as materials scientists is what is the influence of that high magnetic field on the other materials within your reactor? Does that have an influence? And again, this is something that UK AEA are trying to look at when they develop the Chimera facility near to Rotherham as well. So as well as high heat fluxes, they're also going to look at high magnetic fields and the influence on materials too. So in summary, I'm going to go through some of the materials that are going to be used in ITER, so you have an idea of what materials we look at. These are not necessarily the best materials that we could use for a fusion reactor, but that's what's been decided for ITER. And going forward, we might improve and develop new technologies as well. Well, we should. That's the aim. So for the cryostat, which is basically the giant fridge that holds everything together, it's going to be made of stainless steel, so kind of fairly standard, well-established material, and that's the same case for the vacuum vessel. That's also going to be made of stainless steel. I think 316 out, if anyone is a steel fan out there. And then the diverter region here at the bottom, which I mentioned, is like the exhaust of the tokamak. That's going to be made of tungsten. Following that, we're going to have a blanket made of beryllium in ITER. Now, beryllium is quite toxic, so I think there will be a movement as we develop new reactors not to use beryllium for first wall, and maybe use other things, maybe tungsten as well. But for ITER, it's quite a an established material, so it will be used. And another cool thing that is meant to be done in ITER is that some of these blanket modules will be substituted so that they can test tritium breeding within the blanket modules. So can we use the fusion reaction to generate more fuel as well, which is something that's not been done before, and ITER will look to prove that. And again, huge materials challenges there. And then finally, for the supercooled superconducting magnets of ITER, they plan to use niobium tin or niobium titanium magnets as well. But as I said, there's also been investigation for other reactors to use different materials, so these high temperature superconductors. I realize I've spoken quite quickly, but hopefully I've kept to time, and that's kind of just a summary of the main materials challenges. I'm going to be on the Manchester stand as well afterwards if people have any questions, either about materials issues or Manchester projects as well. But thank you very much.
Thank you very much, Annika. Hopefully you found that talk stimulating as the other talks. I certainly did. We now move on to our final speaker of the webinar session, and that's Dr. Heather Lutus. Heather is a colleague of mine at UK AEA, and she's going to talk to you about fusion engineering challenges.
Hello, everybody. It's really nice to be able to talk to you today, to give you I would say a flavour of all the different engineering challenges that there are that we really need to solve if we are going to meet our aims of commercial fusion power. So what I'm going to do today is very much touch on all the different types of engineering that there are exciting challenges about, and then there are lots of people who would be very happy to answer questions about any of these topic areas. And I think a lot of what people have said already feeds, directly into what I've said, which means I don't have to. You've already heard some of the details, so there's a lot already. So when we're looking at a fusion power plant as a whole, there's an awful lot of things that need to come together, from the superconducting magnets to the robotics, to the diagnostics, to the electrical and process engineering. But every one of these areas has complex challenges that we are going to need to solve if we are going to build a commercial power plant which can actually put electricity on the grid. And it's in all of these areas where the engineering challenges are, and where these engineering challenges meet the plasma physics challenges, meet the material science challenges, and it is all very much dependent upon us all working together. So we really need an integrated multidisciplinary capability. So even when working in a specific area, it's very clear that these areas are all related to each other, that they are all dependent upon each other. As Roddy was saying earlier, depending on what the plasma physicists can produce, meets with what the engineers need to build, and there's give and take in both areas. And what this means is that we need people looking at the materials, we need people looking at power plant, we need people looking at how the neutrons behave and the modeling in order to meet this challenge. So I'm going to break this down into a couple of areas, and we're going to start with the engineering of components. And a lot of this is to do with the manufacturing. So Annika's just been telling you all about fusion materials. So now we need to think about what are we going to do with these materials, these many different types of materials that we need to be able to use. What we need to be able to do is we need to build things out of them. We need to be able to join them together in order to build the components out of them. Now that would be hard enough, given the challenges that Annika's just been telling you about, that are written down there as well, all the challenges that these materials need to survive. But then when you're looking at joining them together, you need to consider how those joints are going to be weaker than the bulk material, what effect that's going to have. So there's a lot of engineering challenges to do with how you then take these materials, how you process them into the components that are going to build your reactor. So these materials, building up these components within your tokamak. So then the question is, what's what in a tokamak, and Howard was showing you that in the first presentation. So what I'm going to do here is just take two examples. There's complexity everywhere you look, but two particularly complex examples to show you how the different types of engineering are needed, and all the questions that we've yet to answer that we need people to come in and we need people to be researching. So in terms of what's what in a tokamak, you've got jet here and you've got ether here. Both you've got the first wall and you've got the magnet systems. So those are the two things that I'm just going to touch on right now. So the first wall and a breeder blanket. So in the component where we need it to survive, being that plasma facing component, but within the same component, we need it to be able to breed tritium. So this is a particular component which we are asking an awful lot of. So within this, we need it to survive the operational loads. So we need the first part of it to be able to survive the thermal, the radiation loads, and in the magnetic fields. So we have that armor material. What we also then need to do is for that to work well with everything that's behind it. You could build an armor material that doesn't let any sort of neutron through, or you could try. The trouble is you need some of those neutrons to come through, because behind it you want to breed tritium. And to breed the tritium, you need the neutrons to be able to get through. So all the different parts of this need to work together, and you need to engineer it so that it works on all these different levels. What it also needs to do is it needs to be a shield. It needs to be a shield for the radiation environment. So you've got this component, and then you've got everything that's behind it, including the magnets. And ideally, you don't want them to be exposed to the same level of neutrons. They're going to be more delicate, and you want to try and protect them. So you're asking these components to fulfill multiple functions. So you're asking it behind that plasma facing bit to generate tritium. Okay, that's great. Then you need to be able to get the tritium out of it. So not only do you need to have this component designed so that you can hold the tritium breeding material, that you can get the neutrons to it, that it can survive in the environment, but then you need the systems that are going to allow us to actually extract the tritium in order to then put it back into the system. And if that wasn't enough, the whole point of our fusion power plant is to extract energy. We want to be able to extract that energy to create the electricity. So we need to be able to usefully do something with all that energy, all that heat, which is impacting on these components. So that heat that you're trying to protect everything from, you also need a way to use it in order to turn a turbine, in order to generate electricity, or to produce that useful electricity in some way. So there's a lot of things that we're asking these components to do, some of which are mutually exclusive. And there's some really exciting engineering in coming up with the ideas for how this can work. So the second component I want to talk to you about is the magnets. So the magnet systems, I'm going to particularly talk here about the superconducting magnet systems. So it was explained before that we're using magnets to confine the plasma. You've got different coils, you've got ploidal, and you've got your toroidal field coils, and they act together in order to confine your plasma to try and keep it away from the walls. So if you want to generate this magnetic field using superconductors, you have to think about the engineering on these different scales. You have to think about the tape. So there's an awful lot of physics, a lot of material science going into the superconductor research, but then there's the engineering of it as well. So you've got the conductor, you've got as a tape potentially, fine, but you can't wind a tape just round in that coil by itself. It needs to be protected, it needs to be cooled. So you need to create an assembly which this can be packed into. And there's an awful lot of complexity just in that. How do you protect it? How do you make it flexible? How do you fill it with some sort of non-conducting system in order that it doesn't move around? And then when you've got a cable, you then need to pack it again into an assembly. So you're going from something on a scale of that conductor to something on the scale of the pictures on the right, which are the ether coils. So you've got to consider that engineering over different scales. Applied physics, chemistry, engineering, it's all on a spectrum. And you need to work on it across this length scale as well in order to produce something which is going to be useful in a reactor. So those are just a couple of components which have some really interesting engineering problems. So that's what's right in, the center of your power plant. That's the sort of business end, that's your tokamak. But then you have all the other systems around it, or the systems that you are going to need to work with it, where there are also extremely important challenges which are going to be just as essential to being able to produce a reactor which produces electricity. So, for example, the electrical and process engineering of this. So the infrastructure that's going to be needed to extract that heat load is going to be really complex. So, for example, at the moment, JET uses 1 gigawatt of electrical power. And in an ideal world, we would be able to reduce that for future tokamaks. but it's still going to be an awful lot. So how do we design a system that really reduces that as much as possible? How do we design a system so that we can make sure that we get more heat, more power out than we need to put in? The process engineering of this is extremely important as well. So everything we've been talking about requires coolant of some kind. You have coolant loops pretty much everywhere, needing to be doing slightly different things, but coolant loops nonetheless. How do you look at the process engineering of this? How do you look at how those coolant loops interact with their environment, how they help with processes like tritium extraction, in order to allow this whole system to work? When you're talking about tritium and how it's used within this system, this is another area of research. It's an area of research which we do a lot of at UKAEA, and it's extremely complex. Getting the fusion into the system is a whole engineering problem. Getting tritium out of your breeder blanket materials, out of your coolant systems, is another problem. Every little point in this diagram is an area where there is ingenuity needed, where there are different ideas and solutions that are going to be needed in order to make this work as a sort of an optimal power plant. Right, so you've got your power plant, it's working, but in order for it to be accessible, in order for it to be maintainable over a lifetime that's going to be cost effective, basically, you can't have a disposable you can't have a disposable reactor. You need to be able to remotely maintain it. So this is where the robotic operations come in. The picture at the top is JET a while ago now, so back in the 80s, when any sort of maintenance was done by hand. Now, there's a lot of good reasons why you don't want to do this. There's a lot of hazardous materials. When you have a power plant that is on for a long period of time, there's going to be high levels of radiation. So in order to reduce these risks, you want to be doing this with remote handling equipment as much as you possibly can. So there's the UKAEA, the RACE department, so Robotic Applications for Challenging Environments, which takes the knowledge learnt in operating JET and doing remote handling on JET, and takes that further, is always adapting it, and is also looking at how you might apply this to other applications as well. And there's a lot of things that go into this, lots of different types of engineering as well. You've got your cybernetics, you've got your software architectures, you've got everything that you need to think of in how you will create and control these systems. How are you going to sense where they are? How are you going to prove that they have carried out the procedure that you've asked them to do? So there's a whole engineering piece around that remote maintenance. Right, so you can build what you like. You could come up with a fantastic way of manufacturing something, but if you can't prove that you have manufactured it, that you've created it to a certain standard, no one is going to let you put it into a fusion reactor. So we need to think of ways to test our materials, our components, our systems, to inspect them. We need to be able to control our robotics or our diagnostics, and we need to be able to qualify that all these parts of the procedures are behaving the way that we have designed them to be doing it. Now, the very nature of a fusion reactor and the materials that we're going to want to use in a fusion reactor means that our job is much harder in these areas. So, for example, we have made a component out of tungsten, one of the materials Annika was talking about, an extremely dense material. If we are looking for defects in this material, its very nature makes it harder to detect them. And then what we're going to do is we're going to stick it in a high magnetic field radiation environment. It's going to mess with the electronics of all our sensing devices. It's going to mean that we've basically just made our life much more difficult. So how do we design ways of inspecting these materials to look for defects that are going to be able to work not only with our materials, but with our geometries, can be put into the vessel and used with robotic handling equipment? How do we take all that complexity and make it work for this sort of inspection technique? And there's a big area of engineering and of science in doing this. So the areas of testing validation, they span the length scales. So large science experiments, so beamline experiments come into this at one end of the scale. We can go and take our prototype components, our new materials, and we can go and inspect them at beamlines, really looking at the fundamental detail of what we've got, looking at it really at the scale of using neutron and X-ray beamline experiments. And there's some really exciting projects and opportunities and need for this sort of technique. At the other end of the scale, you have the Chimera experiment. So this is what Annika was talking about in terms of high heat loads that are going to be in the Yorkshire facility. So this is a unique test facility that they haven't, it's designed, it isn't even built yet, which is going to allow us to look at 4 Tesla across components. So the unique thing here is we're going to be looking at it at sort of meter scale. So then that becomes, how does your material on a small scale behave in a magnetic field under a heat load? But then how does it do it when you put a component together? How does the bit of tungsten that you've joined to the bit of copper that you've joined to the bit of steel, how does all that behave as a whole system under these loads? So there's going to be the high heat load, the vacuum, and the magnetic field. And so this is a whole big engineering project that will be turned on in the next couple of years, and that we are going to need people to come and work on, and we're going to need test pieces that are going to be a big part of this research. From a more computational based point of view, you have the Neutronics. So looking at what happens in the radiation environment. So mapping what happens with the neutrons and modeling how within the different systems, so you have a new design for your tokamak, how does that change the way the neutrons behave? How does it change where they go? And this is incredibly important because it needs to be fed into the design. You need to know what your nuclear what the nuclear data is going to show you, so that you can design your components to fit their environment, so that you design for what the neutron, what the radiation these components are going to see. So what's fantastic is within the UK, we are experts in a lot of this, from the robotics to the testing, obviously the plasma physics, the tritium, all parts of the engineering and science. There are areas where you have expertise and that works with expertise across the world in order to really be at the absolute cutting edge of all these different areas. So it's a really exciting time to be involved. There's also really fantastic opportunities to engage with industry and to engage with other sort of research organizations. And this is just a flavor for some of the organizations that we collaborate with. This is only a small part. This is a drop in the ocean in terms of the sorts of organizations that it's possible to collaborate with, learn from, and bring that information into Fusion. So I just wanted to finish with saying I have done a very speedy way through in terms of the technology challenges that are out there. They are complex, they are diverse, and they are really exciting. And what's particularly exciting is what happens if we solve them. That's the great bit. And there is a problem for any discipline. There is a problem for every type of science and engineering that needs to be solved. And we're in a great position to do it. We need new ideas, we need new ways of looking at things, but we're in a great position in order to solve these and really move forward. So that was a whistle-stop tour through fusion engineering.
Thank you very much, Heather. So I hope that the participants have enjoyed the talks this afternoon and found them stimulating. And now I encourage you to make best use of the rest of the afternoon. It's not often you get the chance to get 8 universities in one place and have an opportunity to talk to them about the opportunities for MScs and PhDs. Don't forget, you can also join the student chat room and find out what life is really like as a PhD student. And also another reminder that there are some virtual tours of the fusion facilities at Cullum at 3 o'clock and 4 o'clock. There's 2 different tours you can do, but you may just choose one that's most appropriate. Certainly make sure you find the time to visit the university stands. It's a great opportunity, and good luck in exploring opportunities for doing a PhD and MSc. I think that's the end of the webinar session. So this session will now close. As I mentioned earlier, we will try to address all the questions in the Q&A and email the answers out to you. Most of them have been addressed, but there's still some coming in, I see. And we'll address those and get back to you. So thank you very much, and I hope you enjoy the rest of the afternoon.